This lecture is being brought to you in part by the generous gifts of these sponsors.
Thank you very much, everyone. It was great for the introduction. I'm happy to be here. Didn't have to come very far, as he said. I'm from here, and it's been an honor to be able to work here at IHMC and in Pensacola. A little bit about me. I don't feel like there's much to add after the wonderful introduction I just received. But the one thing I do want to highlight is Pensacola is a fantastic place. I've been here since 2016, and part of that has been the love of the community that we have here. I feel like IHMC plays an important part in Pensacola, but I feel like Pensacola recognizes that as well, and they play an important part in IHMC. So it's been an interesting ride. I've gotten to see the change from exoskeletons and humanoids as research platforms. My PhD was focusing on shipboard firefighting, which you can actually see up here on the right. That was actually over in Mobile Bay. There was the ex-USS Shadwell, where they trained all of the firefighters on board ships, and we got to take a robot down to help do that. And to go from that to where we're talking about today with humanoid robots doing commercialization, potentially being applied in all sorts of different ways throughout society. It's been really interesting to be able to do that, and so I think that gives me a little bit of a unique perspective to be able to talk about some of these things. But before I get going much further, I do also want to recognize one of the other excellent things about working at IHMC is the team that I get to work with. It's an honor to get to come to work every day and work alongside people that work incredibly hard, are really dedicated, and I get to take the spotlight in situations like this, so I want to make sure to give a little bit of that to them, because without them, none of the work that we would have, none of the work that we do would be possible, and they also make being able to come to work every day fun. Please. And then it's also good to note, we do a lot of things in the robotics lab that aren't humanoids. So we do exoskeletons as well, we do drones, human-machine teaming, even quadrupeds. You're not really going to get to see very much of that today, but you can look at our YouTube channel, you can come to our open house in April as well if you want to see some more of these things in person, be able to maybe interact with some of them as well. But today we're really here to talk about humanoids. And for me, a lot of it is what is the motivating factor? And it's that the robots that we have today, in a lot of cases that are actually deployed, they just don't work in complex environments. If I talk about different applications like emergency response, even soldiers, or even just manipulating these operating panels, there's a lot of mobility challenges, there's a lot of other challenges for these robots to get there. They simply can't operate in these terrains. And that really limits their total application. And if I think about some of these obstacles, it's things like doors, control panels, ladders. A lot of these robots are built to do one or two things. Amazon warehouse robots are a great example of that. They can drive around the floor. They do that very well, but they just don't scale to a lot of these other applications. And that is really why humanoids. We have humans doing all of these tasks, and I want a robot that can go where people go and do what people do. And, well, in a lot of cases, that necessitates a robot that looks somewhat like a person. The world that we've built is designed for people, by people. A great example of that is the fact that the Americans with Disabilities Act exists. The ability for people that are wheelchair bound to be able to get around is only possible because we have the ADA, and even then it's still very limited as to the type of places that they can reach. There's a lot of issues for this access that continues to be a problem, even despite the great efforts that we've made on that. And so if I think about trying to extend robots into environments that are designed historically just for people that have only been accessed by people, it's going to be a real challenge if I'm trying to take a traditional platform to do that. We can actually highlight that really simply by kind of comparing. So we have our robot here on the left, Alex. Next to that we have a quadruped, Spot, made by Boston Dynamics. Then you have the robot, you actually walked by it on your way into the room here, T-Bot. We can do a little bit of a throwback there. And then there's the PackBot that kind of gained popularity. It's one of the first mobile robots that made it out there. If I look at these different platforms, if I talk about squeezing between a narrow space, you can have a pretty big humanoid do that because it can turn sideways. You can, you're skinny where you need to be, maybe not as skinny as we used to be, but you can still get there. But a quadruped, you're going to need a pretty small quadruped, but not too small, shoulder width. But your wheeled base and your track base, they have to be quite small. It's really that width that limits them. But then if I think about stepping over a barrier, I can step over a pretty high barrier because I have long legs. I need a pretty tall robot dog if I wanted to do that. And then For your wheeled and tracked ones, it has to be quite large. And the same thing kind of extends to other tasks that you can imagine. But then there's some things that you simply just can't do with a wheel or track-based system. Things like stepping stones or climbing ladders. You just can't do that. And so if I want a robot that can go into a place that has that as a challenge, I really need to have something with legs. And, I can actually take a video that was filmed in my former colleague's garage. We like to say that this is like a disaster zone. And you can see if I want someone to be able to go in there and get an object out, he's squeezed between some tight places, take a big step over. Never mind that he's wearing flip-flops. That's probably questionable safety. He steps across, goes over a carpet, all to get a tennis rack. And while this may be a pretty trivial example, it's still, you can imagine, a quadruped probably couldn't do this. I know a wheeled or tracked robot couldn't. Maybe I could fly a drone in, but that's going to be limited by however much it can lift, which isn't a whole lot. And so you can see why, if I have these hard-to-reach places, I probably want something like a humanoid. But now we can kind of look back as to, well, what funding got us to where we are today? A lot of it came from government funding. A lot of our investment in this research and development process came from government-funded research. It's important to recognize that. A lot of the innovations that we have today were supported and made possible by government-sponsored research, and humanoids, quadrupeds are no exception. You can actually trace this back. If you go into the IHMC lobby, we have an M2V2. That was around 2006 to 2008. But it really started to strike more of a high-speed progress when DARPA stepped in and started funding the Big Dog program. So that's this quadruped that you see down there from Boston Dynamics. Early day footage, you can find it online still, people shoving it on ice, doing all kinds of crazy stuff. And then, this just further increased. You had programs focused on carrying larger loads, like the LS3 program, which led to this huge quadruped. You had Petman, and then a really interesting one was the M3 challenge, which actually funded a couple of different teams, including MIT. They really focused on this like high-speed quadrupedal running, as well as IHMC, where we were focused on bipedal running. So we actually that led to the Fast Runner robot that we ended up having a Hex Runner, which somehow is making a resurgence on the internet from videos. People are acting like it was this year. That was literally over 10 years ago. But we took it down to the airport, had it run on tarmac around 37 miles an hour. So there's a lot of things there that has been supported by this investment. And this kind of led, the pinnacle of a lot of this, in my opinion, was the DARPA Robotics Challenge. I don't just say that because IHMC came in second, but it really was one of those challenges where the competitors in it didn't know exactly what they had to do. They knew in the abstract the tasks, but the exact specifics of the task weren't set. They could be varied from thing to thing. And it was done in response to the Fukushima nuclear disaster. Where the idea was, well, if you could send a robot in, that would have prevented a reactor meltdown. And the thing that was particularly impressive about that to me was the fact that you had to show up at a specific time and do those tasks. You had an hour, and that was it. If you couldn't do it at that time on this day, you didn't get any points, and you wouldn't win. And that's not exactly what we're even seeing today with a lot of the demos that you see on these humanoids. Those are very, we'll talk about it a little bit more later, but I have a film crew coming that kind of constrains the day that I'm in, but I get a couple of takes. But it is interesting because now humanoids aren't just research. We had all this early government investment in the research, but it's not just research anymore. Now there's a lot of startups. This obviously isn't an all-encompassing list. If I were to try and list all of the companies from China, it would probably be the rest of this presentation. But you have the high points like Boston Dynamics and Agility Robotics, and you have a lot more on this list as well. And a lot of this is not necessarily driving at the appeal from the mobility of these systems, but it's the big workspace. So you think about a humanoid can reach down low, it can pick something up off the ground, it can also reach up high. And if I'm thinking about a robot that can do that, that's genuinely challenging for a lot of systems. And so humanoids are really good for that. But most of the applications today, which we'll kind of walk through in a second, are really focused on more simple, repetitive tasks rather than this complex thing that we're really hoping humanoids can fulfill. It's also worth noting that, as far as I'm aware, the only real company that I think is delivering value to customers today is Agility Robotics. You have a lot of other companies that have raised a lot of money, They're talking about deploying robots, and I think a lot of them are probably on the cusp of it. But the only one that's currently sold and being utilized as part of general operations is agility, which is a great segue, because if we start talking about potential applications, one of them could be humanoids for logistics. So here's agility in one of their early deployments at an Amazon fulfillment center. A lot of it was taking these empty totes, moving them back onto a conveyor belt so that it can go back and get refilled by, I guess they're called fulfillment specialists there. And this is an interesting application. I think that there's some questions that could be drawn as to whether or not this is the right task for a humanoid. I have to think about, it's workspace challenged, sure, but probably not really a mobility challenge. Maybe there's some question of why legs, but there's a lot of potential argument there for the efficiency, the availability of work, the ability to move through constrained spaces. And that kind of leads us into some of the arguments being made for manufacturing. This is an interesting one because a lot of what you see robots being targeted for is manufacturing in automobiles. I don't fully understand why automobiles has captured the imagination so much, but that's mainly the thing that people are talking about. You have, on the right, you have Figure AI out of California. They're a startup, kind of one of the most well-funded startups in this space at this point. But they just started a handful of years ago, and here they're working at a BMW factory in, I think, North Carolina. And they're kind of doing one part of the process where it's not time constrained, so it's not the thing that's the bottleneck, but they're moving a part from one place to another, and the work cell closes, and then the task goes. This has historically been done by people. On the left, you have a robot doing kind of the finishing touches and inspection in a facility in China. This is Ubatech. There's a couple of different companies in China that are also targeting this same type of model. One of the other ones that's a little more interesting and is starting to gain a little more common ground on what these companies are targeting is for the home. So this is a company out of originally Moss, Norway, called 1X. They've recently relocated to the Bay Area, and this is the robot Neo in the home. I think that this is an interesting one. You could be pessimistic and say that this is one of the only ways that companies can justify the valuations that they need to be able to get the capital raised to be able to build the production lines. Because if you talk about the total addressable market of the home, it's huge. But I think that there's also a lot of challenges with this. There's the liability component. What happens when the robot falls on someone? Who's in trouble? Then there's the practical component. If I have what can wash a dish a whole lot better than me is the dishwasher. I don't need a robot to do that. And we'll actually touch on that a little bit here in a few minutes. But whether or not this is a great application, I think is up for debate. It's definitely one that captures the imagination, though, because the idea is that you can have access to home care, support, companionship, potentially if you're unable to have additional people come into your home often. There's a lot of potential justifications for it. But we talk about some of these things and we say, well, why humanoids? So I can be pessimistic about it. I can be the naysayer, but I can also play the other side of if you have a general purpose robot that can do all the things that a person can do, that's pretty great because people can do all kinds of things. It may not be the best suited platform for that, but if I have to maintain a production line for one robot, and it can do 1,000 things, that's a whole lot better than maintaining a production line for 1,000 robots that can each do one thing. It allows your economies of scale to kick in. It means that you don't have to actually set up production and supply chain for all these different things. It means that if I have improvements on one platform, it can get distributed across the entire fleet. There's a lot of arguments that make the case for why you should use these robots. I think that it is up in the air as to whether or not that's the right answer. And I think that to some extent time will tell. In a lot of cases it could be that this is a stopgap solution. We may introduce these types of robots to bolster automation immediately, but in the long run, we replace them with more traditional manufacturing that can do higher throughput. Because humans and humanoid robots likewise are going to be limited by the speed in which they can operate. Whereas if you think about a Coca-Cola bottling company, they're not bottling those by hand for a reason. But beyond the applications, I think it's important to look at just what goes into building these robots. And this is the thing that I can probably speak best to. I'm not a venture investor. I'm not leading a startup or anything like that. So talking about the economics of it may not necessarily be my lane, as I'm sure I might hear about online. But I can talk a lot about the design of these systems. And beyond just the hardware design, you have all these hardware challenges of how do you pick out sensors, how do you design structure, your actuators that make it move. There's all kinds of things. I mean, that's the readily apparent one. You look at the robot, and that's the thing that's most obvious. But there's also, well, how do you make the thing move from the algorithm's perspective? What is controlling the desired motions, the behaviors and the autonomy of it? If I need to go in and tell it what to do myself, how can I teleoperate it? There's been a lot of work on that over the years. And then there's the user interface. Well, how do you actually interface with the robot? Is it verbal? Is it via a computer? Is it virtual reality? What are the different things there? All of these are things that you have to consider when you are building a humanoid robot. And first is actuation. If I talk about actuation for a robotic system, this is a particularly challenging part. You really want your motors to be strong. You want them to be low weight. I want, light. I want my whole platform to be light, but they also have to be fast. These are all pretty bounded things. We can do that. We've done that for a long time. What's a little bit harder is they want to be compliant. And what I mean by that is if I physically interact with this system, it should adjust. Traditional manipulators are strong, rigid. If they hit something, they break the thing that they hit. You obviously don't want that if it's around people. But they also aren't very well adjustable to uncertainty. So here on the bottom left, you can see that robot doesn't know that the ground is varying in height, but it can adjust to that because it's controlling that surface compliance, that ability to interact with the environment. The thing that's really hard about this, though, human muscle is great at all of this. Human muscle is powerful, it's compact, it can move fast, and it's very compliant. It's also squishy, which is nice for getting around joints. Actuators aren't that. So that does place a tall order if we want to build a robot around it. We've done this in a number of ways over the years. Kind of the first way that people were really able to achieve compliant control, series elastic actuation. So I know that's a big word. What that means is that I have a motor connected to a transmission. That can be like a screw or it can be a gearbox. And then the part that makes it series elastic is that I then put a spring between the transmission and the output with the world. I put a compliant member, I have an elastic member in series with the motor. And this is great because now I've decoupled the motor motion from the output motion. So if I do something like stomp on the ground, it doesn't load all the gear teeth in my actuator and break it. It also allows me to control those interaction forces. All I have to do is control how much I'm deflecting that spring in order to get that interaction. And we used this on the robot M2V2. I say we generously. I was not here at the time. But I did use it on the robot that I worked on at Virginia Tech. So this is kind of the historical way that people achieved compliant actuation. But it comes at a cost. That's why it's a historical way. They're relatively slow. And one of the things that we care about with balance is we want high frequency control. So I want to be able to control it rapidly. And you just can't do that very well with series elastic actuators. So that's one of the things that kind of enabled athletic motions on these robots was hydraulics. If you've looked at many internet videos over the last 10 years, you've probably seen the robot in the middle there. That's Atlas, one of the Atlases from Boston Dynamics. It's the first robot that really started doing things like backflips. Now, you can ask how useful a backflip is, and I say, I don't care, it's cool. One of the reasons that was possible is hydraulics. So hydraulics are just like what you see in construction equipment. You're putting fluid in, and you're controlling that fluid flow, high-pressure fluid, with a valve, and that goes into chambers on these pistons, and it will control the way they move. And this is pretty great because you can get crazy power density out of it. So you look at these curves, it can be a little bit hard to see. Let's see if my pointer is, so if I have, these are the curves of these valves, and you can see if I care about the velocity versus the torque, I get really high on that. And if I compare that to muscle, that's this other curve right here, it's not quite as good. So you can actually outperform muscle with hydraulics in some way. And historically, electric motors are along here. We've gotten a little bit better. That's gotten a little bit higher, further to the right. But this comes at the cost. Hydraulics are not efficient. So if I want low force, and I'm taking this high pressure fluid, and I'm putting it into a chamber, and I want a low output force, I have to take all of that energy stored in that high pressure fluid, and I have to make it go somewhere else. Unfortunately, my make it go somewhere else isn't back into my fluid line, it is into the form of heat that's just lost. So it's really, really inefficient to use hydraulics in a lot of cases. But you can do some pretty awesome things. More recently, what we've kind of converged to as a field is what's called direct drive actuation. So this is, instead of caring about adding fancy springs on the output or fancy sensors to measure your forces, you just connect a motor to a gearbox that has a low gear reduction, and you're done. And this actually works really, really well. This is a technique that was first really tried out by MIT within the last handful of years on their cheetah robots. So you have a mini cheetah there. This is a picture stolen from the internet. We actually have a mini cheetah on site here, but this has led to an explosion in available robotics. So you can go on the internet and you can buy a Unitree G1 that you can see on the right here for about $16,000 right now. And that's made possible because of the low-cost quasi-direct drive actuation. And that's enabled a lot from the research perspective. It's given this idea that now these are starting to become accessible. That is, again, production volume. So if I'm going to build one, it's going to cost me way more than that, unfortunately. But that's what we try and do here. So we've actually built a number of humanoid robots. So this is our robot Nadia that you can see. This is one of the things that we've been building here over the last handful of years. And we've had these pretty ambitious goals when it comes to robots. We really want to try and match human-level performance. And I'll skip to the end of the story on Nadia. We didn't quite get there. But we got close in some of the areas. We got human-level range of motion, human-level power. We didn't quite get the mass or volume of it, though. And we didn't quite get the robustness either. But this is a really hard challenge. We started on this in 2019, but a lot of these is an exercise in compromise. I think most of your robots, you can get this high level of performance, you're going to have limited runtime. If I can get a really high-performant robot like the G1 that I showed just a second ago, that can operate for about 30 minutes. So that's not great. Not really going to go into a performance line, but that's better than the hydraulic Atlas that I showed, where depending on what you're doing, it got about 5 minutes on a single battery charge. It could run for about an hour depending on what you wanted it to do. So if I'm talking about how do I design to meet some of these requirements, though, one of the first steps is mechanisms. So if I want to take my linear pistons, my hydraulic pistons, and put them in a robot, that requires a lot of really careful engineering. If I want to have these legs pitch all the way up, get that flexion and extension out of them, I have to use a lot of mechanisms. And so we used what was called this dual 4-bar. So, a simple 4-bar is one set of 4 linkages, and we used 2 of them, which is why it's a dual 4-bar. And then each of those is powered by a hydraulic piston. And we were able to get really great performance out of this, really great range of motion. But as you can tell, that's pretty complicated, which comes with a lot of challenges. So it's not necessarily the best path forward in the long run. Another thing that you need to consider when you're designing these humanoid robots is the structure. So earlier I showed pictures of Nadia. We used carbon fiber on that. If you asked me 15 years ago, 20 years ago, if carbon fiber would be a good choice for a robot, I'd probably say no. At the time, you didn't have a lot of examples of people using carbon on durable systems. You did on high performance, so you do in kind of aerospace type domains, but for more durable systems, it just wasn't quite used like that. And then people started using it in downhill mountain biking, which if you know much about downhill mountain biking, those things take a beating. And part of this is enabled by some of the things that you can do with carbon fiber in general. So carbon fiber is typically made with interweaving strands of carbon. One of the great things that you can do is you can actually take it and you can reinforce it with unidirectional carbon. So instead of weaving it in, you can just say, I really want it to be stiff in this direction right now. And that's what we did on the shells here. So we were able to achieve this kind of exostructure that was really, really strong, really, really stiff, and still being really light by kind of optimizing those designs. They even do this in some bicycles, so it's able to actually isolate vibrations on the bicycle just by the design of the frame itself. Now, the challenge of this is I don't want a robot that is shelled entirely in carbon fiber if I'm going to be doing this primarily for physical interaction with people. So if I'm making a robot like Neo, that we said earlier, trying to go into the home, trying to interact with people, I don't want it to be rigid. I don't want it to be really stiff on the outside. And so what you're doing in your design is heavily dictated by your goals. So what 1X actually did on Neo, they have these great videos outside kind of on the internet, kind of highlighting their design. They have this polymer lattice structure that's really cool, makes it soft, and they coat the whole thing in fabric. But that means probably not going to do too well in a heavy industry manufacturing type setting. So you don't have a robot design that will work in both industry, or harder environments, and a home environment. So you do have to choose. Then when I think more back, we're going to tie it back to hydraulics. It's not just pistons. We talked a lot about the pistons, but there's a thing that makes it go, So you can see when we wanted to have Nadia go outside, we had made this giant backpack that takes all of this stuff that actually powers it. You have to have a pump, you have to have a motor for the pump, you have to have a thing that stores all the fluid in it, you have to have another thing called an accumulator that pressurizes the whole system, and then you have to have a radiator to handle the fact that you have to do something with all that heat that you're generating. And on Nadia, we did a good job on the first pass. We still needed a lot more pressure out of it. And this thing was, you can look at it and tell it's pretty heavy. The best in class of this that was ever really been achieved was 5 kilograms per 5 kilowatts, which is really impressive, but didn't include the radiator weight and also is still stuff that I really don't want to deal with on my robot. And so to that end, hydraulics, we kind of moved away from it. I talked about how we started to move to quasi-direct drive on everything, which is really important because if I take these rotary joints, I can get a really high range of motion out of it. I have my high power to weight. I can also just buy things off the shelf. They don't really make very many hydraulic robots, so most of the stuff is custom. And I don't have to deal with that giant hydraulic power system as well as all the hoses that I have to route to my pistons. So you're able to make much more compact, much neater, much more presentable designs that look less like something a mad scientist came up with in a lab, which is great and actually led to the design of our robot there on the left, Alex. Kind of the core part of Alex, though, is, again, we're going to keep on this theme of actuation. For us, we really focused on quasi-direct drives, doing a different take on it than a lot of other people do. So we wanted to use a different transmission called a cycloid. And the reason being, on a traditional planetary gear, you have all these interlocking teeth, and those teeth are going to rub together. So you have all these losses that come from the teeth rubbing together, which is unfortunate. It introduces friction, you get backlash, which makes it harder for control. Friction means that you have all inefficiencies. It also makes your ability to do higher reductions worse. So then your whole actuator is operating less efficiently. On a cycloid, though, here I can actually take each of those contacts and I can put a bearing on it, which you see here on the right. If I have a bearing, that means that I'm not rubbing. The whole surface rolls. And so, we took one of these actuators, and, pretty big, but we gave it to one of the engineers, had his son come in, and he was able to just backdrive it by hand, which is almost unheard of for things of that high of power. Really, really low backdriving force, which means you then get efficiency, your transmissions hold up longer because they don't rub and wear out, and then you can actually have your whole system operate for a longer period of time. But beyond just the actuators, if you're designing a robot, it's not just about the motors, it's about what can the robot do. So for that, you really want to focus on workspace. We talked earlier, a lot of people care about these robots because they have these big workspaces. Well, how do you maximize it? What are the kind of tools that we use as roboticists to do this? A big part that we do is these workspace analysis things. So it's a pretty diagram, which I'll give it that, but what does it mean? So I like to use heat maps, which is a questionable decision since I'm also colorblind. But if I look at this figure, the way that I interpret it is, the further I go to the right on my color gauge, I'm not going to attempt to say what color that is, I think it's blue, the more poses my hand can achieve, which means the more ways I can grab something at that location. And if you think about that, that's really important, because if I can only grab something from one configuration, I can't do much with it at that. So I really want that thing to be most dense, to have the most number of poses, the most blue, in front of the robot. So that way I can also grab it with both hands. And you'd think that this is obvious, but it's not often done. And I can say, for example, a robot we used to work with, Valkyrie out of NASA Johnson Space Center, they designed the robot. They were very rushed at the time, so I'm not going to be critical. It was part of the DRC. We didn't have all these tools. The workspace is pretty much to the side of the robot. So the best way to interact with the environment is to stand sideways to it, turn your head, and grab something. It's not really ideal, one, if you want to have it operate like a person, and two, if the task takes two hands. But it goes beyond just the arms. It's also the legs. We're talking about legged locomotion, legged robotics. This is something that we care a lot about at IHMC, and I think that a lot of the industry also should care about, but they don't always, is the natural dynamics of the system. So if I'm swinging my leg, that has dynamics. What are the motions, the forces that are required for it to move? And what you can actually look at is the more mass you have towards the foot, the more distal the mass is, the higher the torques you need at the hip. The bigger the actuator has to be, the less efficient the whole system is. And this makes sense. If you've ever worn ankle weights and gone on a walk, you can tell that it matters a lot. So you really want to reduce what we call distal mass. And it's interesting because you can actually go out, and I feel somewhat bad about this. I usually reference Figure. Again, we were talking about startups earlier. Their ankle design is the exact opposite of what I would want to do, where they put as much mass towards the foot as they really could in that design approach. It's easier to do that, but it makes for a less performant system. That maybe doesn't matter for their goals, but if you're trying to make a robot that can move through the environment efficiently and dynamically, it matters a lot, and that's what we're trying to do. And, part of that is also adding a battery. I don't even want to show the picture of Nadia where we put a battery, because you add a battery to the back of that giant backpack pump as it was, and now the thing's going to fall over backwards. But we designed Alex to be able to incorporate a battery directly, and there's a lot of different ways of doing this. There are companies that design them completely integrated. Figure does that. So they just use inductive charging. They don't have a swappable battery. But, in my opinion, the swappable battery is really convenient, because then I can pop it out, put a new one in, and I can keep going. Or, like some of these robot companies are doing, the robot can take the battery out, put a new one in, and keep going. So, and, when I put all these things together, I can make robots like Alex. This is us walking at the tech park back in November. It was the first time we've taken a robot out of IHMC in about 10 years since the DRC. It's the first time we've ever taken a robot built by IHMC out of IHMC. And you could also make the argument it's one of the only times that the tech park has been used for much tech. But the question is then, how do we do this? We've used a lot of what we call simple models at IHMC. This is one of the ways that everybody used to do it. And it's one of the ways that we've advocated for pretty strongly for a long time. We're starting to relax on that, which I'll talk about in a minute. But the great thing about walking is you can describe it in really easy ways. Basically, it's an inverted pendulum. So if you've ever tried to balance a broomstick on your hand, that's pretty much how robots balance. You have a center of mass at the top, so basically where all the mass is on the robot. You also call it a center of gravity. And then you have a center of pressure, so it's where you feel all the forces going through on your hand. And if you think about balancing, as the pendulum, as the broomstick starts to tip, you move your hand. Right? Well, that's the same thing you do as a person. If I lean forward, if I move my center of mass forward, my weight shifts in my feet, which moves my center of pressure towards my toes, moves towards my heels and the back. So that's standing balance. Well, walking is just moving that from one location to the other. You're just moving your weight distribution, your center of pressure around to manipulate your center of mass. And the great thing about using these reduced order models or these simplified models is that I can use them in all kinds of different environments. There are those that will argue that they don't apply to more complex terrain, in which, we make some simplifying assumptions that relaxes that, but you can still use them, and we've demonstrated that at IHMC over the years. But it's also, to me, if I'm going into these unknown environments, it's really important for me to be able to interact with the robot, predict what it's going to do if I tell it to do something, and be able to modify what it's going to do in an easily interpretable way. And I can do that with simplified models. If I'm having to think about how the elbow is in order to make it walk, I'm missing the mark a little bit, and I'm not going to be able to have that kind of flexibility. And the great thing, this enables robust walking. This was me in 2022, I think it was, without the beard, so more like what I look like in those pictures. I joked that this was my mask, my disguise, so that nobody would ambush me before the talk. And I was excited because this was the first time I worked with a robot that was fast enough for me to actually do push recovery. I worked with Atlas, a different Atlas before this. It was a giant, slow robot. You couldn't do this. And then I worked before that with the one from Virginia Tech, and it was also slow. And so we couldn't really do this kind of testing of these models, and they work. And we use it on all kinds of different terrain. And this is it picking the feet very carefully and then moving them to maintain balance. You can do the same thing where you just say, walk at this speed. You can make it more dynamic. And there are examples of robots walking even more dynamically than this. But this is my presentation, so I'm going to show my robot. And so these work very, very well in a lot of different environments. In fact, you can even do things like applying external forces on the world, using your simple models. So if I want to, let's say, gain access to a building, let's say the building's on fire, but the door's locked. I'm a fireman, I need to get in to rescue some people. I'm going to have to kick the door in. Well, I can do that with a simple model. I can say, here's the force that I need to exert on the door. Let me back out my center of mass trajectory in order to do that, and I can control to do it. And I'm not just saying that you can do this, we've actually done it. And this was probably the most fun day that I've had at work before, where we set up a door. This is an actual locked door. The robot sees where the door is, knows where it needs to stand to kick the door in, and positions itself and then does the kick. And this is an actual locked door, and it's actually kicking it in, which you'll see here in just a second. You can see the hasp on the door latch flying off. Here's where it is. You'll see it kind of go flying. And I guess I added the cinder blocks for more dramatic effect, but than anything else. But this was also a day where I learned if you're ever going to do this, get solid core doors. The first time we did it, the door was in half by the end of the day. But you know, a lot of these are kind of contrived scenarios. Walking on flat ground, sure, I can do really aggressive stuff with simple models. Even walking on some more adjustable terrain, I can do some pretty impressive stuff. But you don't get quite that level of robustness. So what's next? What we're kind of seeing taking over are two different approaches. You have reinforcement learning, and you have trajectory optimization, where in reinforcement learning, let's say you have some policy, which I'll call pi here on the left-hand side. You can call it whatever you want. And then I have some cost where I get a reward. Let's say I do the right thing, you give me a cookie. And I want to maximize the number of cookies that I get. So I'm going to adjust the thing that tells me what to do in order to get more cookies. And that leads to these quadrupeds walking there on the right. And you can train them in simulation, and it's great. And then another option is trajectory optimization, which you can see here on the bottom right, where I'm trying to compute what I should do based on minimizing some cost. Which you could also say is I have a pot of cookies, and if I do the wrong thing, you take it away, and I'm trying to keep the number of cookies that I have. So these are, the thing that's important here is this is computing it offline from simulated physics. So what you can see in the top right, I'm simulating these physics to compute the reward that I'm going to get. Or in the bottom right, I'm computing this online from physics that I was told, but it's the same problem at the end of the day. You're just optimizing one offline and getting kind of a fixed policy, and the other one you're computing online. So at the end of the day, a lot of these are solving the same things, just doing so in a little bit of a different manner. You know, you can argue about some of the nuances. One is learning from past experiences and encoding them into its actions. The other is computing what will happen in the future. So you can maybe get some more reactivity, but it also can't consider everything. Important part is the top one also considers probability. It's all based on statistical likelihoods. The bottom one is more deterministic. It's saying, well, what will happen based on this? And obviously, you can't fully model things. But this model predictive control that we call trajectory optimization, it's great, though, because it obeys the physics of the system. It will give you an output that is bounded by the physics that you told it. So here is an example. You know, a lot of the videos that with Atlas that we showed, it uses this MPC approach, and it will execute the outputs, where you can tell it a lot of different things. Here on the bottom is us doing some earlier MPC work on Alex. And the great thing about this is you can take all these different inputs. It could be teleoperation input. It could be neural network policies like these learning that we're talking about. Or it can be a gate library, and it will tell the robot what to do, and it makes sure that it obeys those physics. Whereas reinforcement learning, honestly, is a lot simpler in a lot of ways. Here, you know, we worked on this for a little bit, but I can download some open source code, and I can get my robot Alex to walk with some tuning. But I don't have to write this massive amount of code. You can do this in a couple hundred lines of software that, honestly, at this point, you can probably ask some LLM to write for you. As opposed to the MPC libraries that we were talking about, that's tens of thousands of lines of code. You get a lot more flexibility with it because it's not only based on its past experiences, but it also introduces a lot less room for error when I have less code there. However, like I said, it's very dependent upon its past experiences. So if I don't have a lot of experiences walking slowly, what you can get is these results like here on the right, where it looks horrible when I'm trying to tell it to walk slowly. It starts to look a little bit better as it gets towards the end. It starts getting faster, but it is really heavily based on the experiences that it has. But you can still get some really incredible results. I don't advocate for kicking your robots like this. I also think that this is very promotional dependent, But you can get really robust movements out of this. It's basically switching between two things. One, do the stance routine, and if you fall, stand back up. That's all that's going on. And it's able to recover incredibly impressively based on having been trained on that. But you don't get a lot of flexibility. So this is one of the things we've spent a lot of time working on is mechanisms for getting high flexibility in unknown environments. So here I have my operator, John, who's in the background. You can't see him, but he's in a virtual reality headset controlling the robot. So he sees what the robot sees, and then as he moves his hands, the robot does that. And he goes over, he picks up this pipe, and he'll pop open the thing of this barrel, which is something that if you didn't know how to do that ahead of time, your robot wouldn't be able to figure that out based on past experiences because it doesn't have those as experiences. But a human in the loop can just look around, see tools, identify how to use them, and just do that on the fly, which is really important if you want robots in high situation tasks like, in this case, we're looking at bomb disposal. So if I don't want to be relying on something that has that level of uncertainty in there. I want that tight control. One of the other things, as a little bit of an aside that we learned in this, is make sure to tell your cleaning staff that you're going to be having a fake pipe bomb, because if they walk in and that's sitting on the stairs, you get some phone calls. But VR isn't just for these relatively slow tasks like you saw on Atlas. You can also do things like ping pong. So here we have Luigi Pinco, one of our research scientists here, playing ping pong against Dexton Anderson, one of our other researchers in the background, who you can see he's wearing the headset. This introduces challenges. You got to get over the latency. So you have to be able to get the data to the user. He has to be able to figure out what the heck's going on. So where is the ping pong ball? And then tell the robot what to do, and then it has to respond to that quickly enough for this to be effective. So that's one of the reasons we liked this as a challenge. And you can actually do this with VR as well. But beyond just that, if I think about mobility, a lot of the situations we've been trying to put our robots in is this kind of complex terrain over the years. So for Atlas, the way that we did this, you would have this one LiDAR on the head. This is a, at this point, 20-year-old sensor. And it would build up this model of the environment, and then you could plan the footsteps that the robot would take over that environment, which is great. It works really, really well. As you can see, we have the robot here in preparation for an open house, just go up and down for about 4 hours. A person is just saying, climb to the top. It figures out the steps, as you can see on the bottom left, and the robot then does it. But the problem with this is it's not very adaptable. If one of these cinder blocks drifted while the robot was in the middle of going up those steps, it would keep saying a step there and it would fall. So to that end, we spent a lot of time. This is one of the great things that GPUs have enabled. You can do a lot faster computation. So here's Nadia actually going upstairs, and you can see it's computing these steps as it goes. And it's also mapping the environment as it goes. It's not waiting for that beforehand. And so it's this idea of modeling the world around it for these robots to be able to walk over. And this is still using those classic simple model approaches, and they work really well. So here we're just telling the robot, walk forward. And when you get to the top, we're going to tell it to turn right. And we'll go over the cinder blocks. This is at the open house in 2024, I think. So we did this then. And you can get really great approaches. It's still not very fast, though, unfortunately. I talked earlier about the DARPA Robotics Challenge and how, I think that it was a really great example of humanoid robots. But one of the things that was a little bit disappointing about it is just how slow everything was. So, they did some benchmarking, and a person could do the tasks relatively easily in about 5 to 10 minutes. I think they had one person see how fast they could do, and it was only about 3. It took IHMC like 45, somewhere around there. Part of that is because just the amount of time spent planning. We showed just a second ago, you can speed up locomotion by just continuously planning. The same thing extends to all these behaviors. So if I look at the statistics, I spent 2/3 of my time with the robot standing there doing nothing, while the operators are behind the scene frantically trying to figure out what to do. So the idea is, well, how can I introduce autonomy to start speeding up the system? This is something that people have been working on for a while. Our initial approach that we wanted to try was, well, what if we have an operator in the loop and make them this critical part of the decision-making process? So that's what you see here. We have John again, John Karff. If you're familiar, there's 10 Karffs at IHMC at this point, and he's actually one of the longest employed people in the robot lab. So they've been a cornerstone of IHMC, and I hope they will continue to do so in the future. So he's kind of dictating the behaviors whenever the robot kicks out of its autonomy part. So I look, and this works pretty well. So here I have Atlas. I told it walk forward. Then it sees a door. We get to cheat here and use a QR code-like thing called an Aruco marker. Sees the door. It says, hey, should I open that? And John clicks, yes. Open the door and go through. The robot goes through, keeps exploring. It sees this debris, and it says, hey, I don't know what to do. So John jumps in with VR, and he's able to move these things out of the way. And this is what I'm talking about earlier with leveraging human cognition. I don't have to have a fancy planning algorithm to do this. And importantly, the planning algorithm might have failed right there. Where the robot thought it was going to do a good job and didn't, he had to recover. And then you go through and you continue the routine. But this doesn't scale super well. I had this kind of rigid autonomy architecture that we showed that we were trying to execute. So what other things can you use? If I want to build higher routines, more autonomy, what can you use? Well, we like behavior trees for that in a lot of ways. So behavior trees were invented by a researcher from MIT, formerly named Rodney Brooks. He also went to go on to found iRobot, who makes a lot of vacuums, as you've probably heard of them. And then Willow Garage and a lot of other robotics companies, also after directing an entire department at MIT. So he knows what he's talking about. The great thing about behavior trees is it allows you to kind of nest this structure. So at the end, the leaves of the tree, as you will, are going to be these little actions. So things like turn a handle with your hand. So I tell a right hand the motion what to do. Well, I can compose those up the tree. So here I have a door opening one. So this one's turn the hand, and then this one is reach with your left hand to the panel. Well, that is the open door portion of it. Before that, I need to reach for the handle, and before that, I need to walk to the door. So you can just kind of compose up as you go, and each of these is a different node. And the great thing about this is I can nest these together. So if I have this, I can call this my door opening behavior in my behavior tree. Well, if I want to have an explore room, I can now have a lot of these composed individually to have this whole routine, and it allows it to be this modular and scalable system. And if you design your interfaces well, you can also have humans in the loop. This is, again, we believe really strongly in the ability for a human to partake in this process, because if I'm deploying this into an unknown environment, things are going to go wrong. They always will. And so how do I make it such that that doesn't mean that the whole task is over? So here you can see I can actually look at the nodes that are being executed in my user. It's a lot, I'll tell you that much. But you can see the nodes that are being executed. You can kind of see the motions that the robot's going to try and do before it starts them. Let's see if I can get it to play again. And that allows me to jump in whenever things are going wrong. And importantly, I can even change the motions on the fly. If I'm relying on past experiences, like a trained policy, I can't do that. But people are still using learning more now for this kind of thing. So here's an example. They took a robot and they put it in a simulation environment. And the great thing about this is they were able to vary it over thousands of different types of doors. So they're constructing a virtual world that just consists of thousands of doors. And then they give the robot rewards as it goes through this. And it learns to open the door. The problem with this is the way that you have to get this to work is you kind of basically encode a behavior tree into the reward structure. So it's not entirely different. But the other thing is, I would argue, this doesn't actually know what a door is. It knows that thing that I see in front of me, I should open and go through it. That's all it knows. Which means that it can't really do a whole lot else. It doesn't really have a semantic understanding of the world around it. And then it can't really do anything else with a door. It can't close it necessarily. It can't hold the door open or anything like that. But, learning shows a lot of promise on understanding what things are based on these past experiences. So computer vision is one of the places that machine learning has made the biggest inarguable impact. And part of that is because it's really hard to describe what an image is. Like if you were to say this is an image, well, how do you do that? So this is where computer vision has done a really good job. And here we can actually take these models and we can fine-tune them because there's no way that I'm going to get a pre-trained model off the internet that knows my barricade that we cut in half with a Sawzall is a barricade. So I'm able to actually take that and not start over, but give it these data and be able to use it. And when I add that to these behaviors, you can do some pretty cool things. So here's Nadia 2 years ago where we said, hey, you need to go find the program manager in this building. We took a picture of our program manager, superimposed it on the body of a Marine in uniform and said, go find him. And the robot knows, hey, if there's an obstacle in the way of the door, remove it and then go through the door. And just keep going until you find the person and salute them. And so here the robot unceremoniously moves the trash can out of the way, then opens the door, goes through, and salutes the program manager. Here it's locating where the door is, and it's able to do that because of that semantic perception. And we do this experiment where we moved the cardboard cutout around different rooms, and the robot would continue looking until it found it. And it even kind of culminated in we hid it under the couch over in the corner, and had to move the couch. But I think it's important to note that these behavior trees on their own aren't really sufficient. So I'm usually hard-coding this logic in. We talked about you can compose them into these higher level behaviors, but now I'm having to manually program each possible transition. That's not really scalable and doesn't really model the world around us. I want to be able to control that, but that doesn't work great if I want this big exploration of the world around. So we're trying now, and I think this is one of the things you're going to see a lot of this moving towards in the future, composition into goals and missions so that you have this understanding, but then it's how do you dictate that? So it could be that missions, you can control that things like cognitive architectures, so how do humans think about this, or multi-agent system coordination. And then the individual goals can be managed also with logic systems, or one of the things we tried was just LLMs. And it's also important to note, learned policies fit into this architecture. So if I look at it, I have my tree here and I have this policy that goes, and this is just a behavior. It's nothing beyond a behavior. I can fit it right into this kind of behavior tree architecture. I mentioned that we used LLMs on this. So here we told the robot, hey, go behind the barricade and retrieve the charge from this person, then go place it on the door. Once you have placed it successfully on the door, walk back behind the barricade. And that is the instruction that we gave it. We wrote it in a text interface, and we said, here are the behaviors that you can do for it. And it took those, interpreted it, and encoded it into a set of actions for the robot to take. This works because it had to obey the individual actions that we gave it. So this is something we call in the AI literature the grounding problem. How do you ground the results in reality, something that's capable? And we do that by telling it these are the things you can do. But importantly, if I think about, as we're kind of wrapping up, what is the actual capability of these robots? I think it's important. We've seen, especially recently, some awesome videos of people having robots do things like home tasks. And this is Neo, who's trying to go into the home, and this is I don't want it to be considered knocking on it because what they're doing is incredible and trying to do it, but it's really struggling to close this dishwasher. And the thing about it is this is not what we do, in that this is not a demo that they can control. This is the Wall Street Journal coming and controlling the robot for them. And that's the difference in a lot of cases of the demos that you see online that are released by the companies. That's a tightly controlled environment. I go back to the BMW manufacturing center. That's a tightly controlled environment. I get to release the information on it. But this is what happens when an inexperienced operator, which is arguably who's going to be controlling these things in the future, tries to control it. So if I take this information and I go and review, what can these robots do? Where will they be used? That was kind of the point, the thesis statement I was trying to answer for the talk tonight. To me, there's a big question of how intelligent what we're calling artificial intelligence on these robots really is. You say, I'm using AI to control my figure robot in the BMW factory. It has been on that site for over a month. The engineers have been tuning, you have these application engineers that are tuning the behavior with it to make it work, do these tasks. If you vary the lighting, it may not be able to do it. That doesn't sound like true intelligence to me. I could go and bust most of the lights in this room, and that's not going to affect everybody being able to leave tonight because we're intelligent, we're able to adapt. Additionally, to me, it's important, if you say a task is done with AI or that a robot is using AI, that doesn't mean the problem is solved. This is something that coming from a more model-based background, sometimes I feel like there's a bit of an indictment on what I'm working on because of that, because it's not AI, but AI isn't a magic solution. Saying you use AI, you shouldn't treat this as the problem is solved, because we just saw Neo struggle with an objectively very, very hard task for a robot to do. So I don't want it to be like I'm making fun of them. What they're trying to do is very, very challenging, particularly to have somebody go in and use it that wasn't part of their company. And I think that if we take both of those in context and we say, well, what can they do? They need these really well-defined tasks. And importantly, they need tasks where you can capture the data for how those tasks are done. So again, operating on site at a BMW factory for a month, I can get a whole lot of data of how to do it. And that will help me know how to do this kind of task in the future. So we're not Rosie the robot from the Jetsons. With that in context, this tasks like tote moving make a lot more sense because I can get a lot of data on that and I can define that task tightly. And so I can execute that reliably and deliver real value to a customer. And we're actually pretty close to that as we've shown. And when people talk about how to use robots, what they often talk about are the dull, dirty, and dangerous, the 3Ds. And to me, the inarguable case of this is the dangerous task. And that's really what we focus on at IHMC. The challenge with that is if I talk about a bomb disposal robot, there aren't a lot of those that are needed in the world. Police departments aren't buying a lot of bomb disposal robots, and it takes a lot of money to develop these types of systems. So that's why we're having to focus on more broad applications first. But the thing that you're going to see is things like bomb disposal, in my opinion. This is going to be something that you don't want people doing, period. And you can't just use a different type of robot to do it. Or another example is confined space entry. So if you think about going in and doing an inspection on a chemical tank, that's really, really hard to make a robot to move around in. And also if I'm sending a person in, that person's getting hazard pay, as are the 4 people that's making sure they're staying safe during that task. So it's very expensive, so that actually could be a real market for these types of things. And I think that when we're through the robotics hype, it may be that we do see home robotics. I don't know. I have some skepticism as to the safety of that in the long term and whether it's going to be viable because of that. But what I don't think is arguable, we're going to see a lot of our dangerous tasks being taken away from people because people really shouldn't be doing these to begin with. They're just our only option now. And with that, I'm going to close with a video from also the tech park, but us, beginning to take Alex out and be able to show it. We can have this play in the background while I answer any questions. Thank you all very much for listening tonight. So we have a microphone coming. I think your hand was up first. I feel like there's going to be a lot of questions tonight, so I'm sorry if I don't manage to get to you.
In recent years, there's been a lot of publicity about whether robots should be humanoid or not. You've read articles about that, I'm sure, and studied that. What is your view of the future?
I think that that's a tough question to answer. I think that there are some tasks that I'm not convinced you're going to be able to get away from something with human-like mobility for doing them. Again, that goes back to the dangerous ones. But I think that there's a lot of things that you have to look at from a performance perspective to say whether or not you should be using wheels. To me, carrying heavy objects, I'm already having to carry the weight of the robot with these legged systems. If I can just use wheels where I don't have to worry about that, put giant batteries in the base, that simplifies the problem a lot. And if all I have to do is be manipulating in a less hard workspace environment, I think we're likely to see those replace, as they call them, AMRs, autonomous mobile robots. I think that you're going to see a lot more AMR solutions than you do bipeds. But I think that bipeds do a really good job of capturing the imagination. So it's a very good thing to be able to tell a story about, which is important for fundraising as an example. So that's why you're seeing a lot of that getting captured right now for it. My big concern, though, is how many of these good solutions are we not seeing because the money is going towards humanoids, which is somewhat of a thing I shouldn't say as somebody who works on humanoids. Let's go right here next, and then we'll try and work our way back.
How much y'all use an AI to be translator, communicator with these robots?
Yeah, so that's a great question. We don't use it a ton in a lot of the work that we do. You did see an example of that with that charge placing. So there, I'm typing in, and it's figuring out what to do for that. We're also using it more and more in writing the software, but that's a challenge as well because somebody has to edit that. Often it's me, unfortunately. But I think that you're going to see that more and more happen, particularly as you start to do more natural language processing, as long as you can make sure that the output of it obeys what the robot is capable of. That's one of the big open research challenges. Yeah, so right here.
What do you mean by rewarding the robot, as if you're altering behavior by like in a brain?
Well, it is kind of like in a brain. So in a lot of these underlying systems, they call them neural networks because they're modeling the way neurons in the brain work. It's just a mathematical function though. So in this case, I have something that takes the representation of the system and resolves it into a number that I give the robot. And the reward is that number. So if it gets 2, that's not as good as if it got 10. And so it's trying to maximize the value of that. So it's a value approximation problem combined with a maximization problem. I hope that that wasn't too esoteric of an answer. Let's go here. Looks like the microphone's already going there, so I'll go with that.
So it looks like the main bottleneck is the software, not the hardware. So how long do you think it'll take before robotic brains can be as able to learn and adapt as humans?
Well, I do want to attack part of that. I think that for some of it, the main problem is the software, not the hardware. But that's because we're starting to finally have hardware that can do some of these low-hanging fruit solutions. If I think about, I don't have to go recharge every hour or every 2 hours. So this power supply problem is a big thing, and a lot of that is the design choices that you've made for hardware. However, there's a lot of work being done in this concept that they call it like lifetime learning. Right now, the way most of this works is you get this experience and you don't do anything with it until somebody has trained a new policy offline and deploys it to the robot. The robot's not adapting on the fly. We're currently working towards that. Now, the question of how long until I see these start to be deployed, I think for some tasks, in the near future. I think that for the volume of tasks that we're often being told is going to be much, much longer. And to me, anything that I don't see happening in the next 3 years becomes almost just, it will happen in the future, but I'm not sure when, because that's such a hard problem to predict. Because if you go back 5 years ago, we wouldn't think that LLMs are where they are now. I don't think very many people saw that coming. But you did know this isn't going to happen in the next 3 years type of thing. So I would say we are likely to see these be deployed in some cases in the next 3 years. I think that we're going to have a bit of an awakening as to the actual capability of these as they get deployed. And I don't know if it's going to be a very, polite awakening, you could say. And I think that that's going to see a little bit of an adjustment on some of our expectations. But my hope is that we don't let that discourage us too much, because I think the potential in the long run is still very bright for them.
Time for one more question.
So one more question. Let's go. I promised I'd go backwards, so let's go all the way in the back.
Do you have any type of program for high school kids exploring a career, a major in physics?
So we do have a number of programs. It doesn't always focus on physics. We are a lot more engineering oriented. But we do engage in the Tech Connect program with some of the local high schools where they can actually come a couple days a week and work with us in the afternoons. There's also a lot of other things at IHMC that we do for community outreach. If you aren't aware, programs like these evening lecture series that are made possible because of our sponsors, but also things like Science Saturday, where we have children come in and we actually get them to do hands-on science experiments, and then robotics camp over the summer. So we do try and do that kind of engagement. It's something that we could maybe do more of, but it is challenging because we all also have our research jobs that we have to do in addition to mentoring these students. But that is important because that is a pipeline in Pensacola that we care deeply about.